Assalamualaikum warahmatullahi wabarakatuh. I'm Fatih Arief. I'm the leader of Group 10 for Integrated Project Separation Process 2. And here I will give the introduction for our group. So first thing first, the content of our group presentation will be the CO2 removal and also the H2 enrichment and also the optimization strategy. But as overview, you can see it right here, it's shown right here, and it can be simplified as the significance of hydrogen is growing in addressing global challenge such as energy security, climate change, and the transition to cleaner energy source. It is utilized in transportation, industrial operation, and power production, and also playing a vital role in decreasing the economy's carbon footprint. And this is a continuation of the problem. An optimization strategy for hydrogen production using steam and natural gas as feed from the first SMR reactor, moving on to CO2 removal unit and moving on to H2 enrichment unit into the product. Since our research innovation from LEO in 2023 emphasized the vital role it plays in capturing and controlling the carbon emissions generated during hydrogen production. During the water-gas reaction, the gas stream would mainly be composed of H2 and CO2. This is the reason why advanced CO2 capturing technologies like chemical absorption or physical process are being developed to remove unwanted CO2 from the hydrogen stream. So here our group objective, which is the first one, is implements advanced CO2 separation technologies, focusing on cost-effective and efficient carbon capture, aligned with the latest innovation with carbon capture, utilization, and storage, or CCUS. And the second one of our objective is develop a hydrogen enrichment system that utilize absorption, select the best absorbent material, and suit sample absorption isotherm. And also we evaluate important parameters such as mass transfer zone, column size, column height, and procedure for the desorption regeneration. And the last one, or the third one, is create a detailed plan to reach 99.9% hydrogen purity, integrate cutting-edge separation method like high-performance membrane or hybrid system to improve effectiveness and reduce environmental footprint. For the next part is the CO2 removal unit explained by my partner. Thank you.
Hello everyone, thank you so much for Arief for explaining the introduction of this SMR plan. And now I would like to explain more deeply around the CO2 removal part of this SMR. So the removal of CO2 component in the product are being separated into three main ways. The first are chemical absorption, the second are physical absorption, and the third are hybrid system. The first part, chemical absorption. Chemical absorption with amine-based solvent like MEA method have a drawbacks like high energy requirement for solvent regeneration and for the solvent to lose through evaporation. Lee et al. At 2024 introduced a non-aqueous absorber that made of 3AP and PEG200s, which decreasing water demands, lowering solvent volatility, and improving the thermal stability while maintaining the CO2 capture efficiency. The completely physical process has minimal environmental impact, which is good because there are no chemical waste, and the modular design allows for a very easy expansion in industrial applications. The non-aqueous of 3AP or PEG200 that has been mentioned, system shows that improve performance with lower viscosity, but also excellent regeneration capabilities. These are validated by experiment and simulation studies that the absorption mechanisms involves a carbamate formation, which enhancing the reactivity at low partial pressure. On to the second way of the CO2 removal, which is the physical absorption. Briefly, physical absorption is working more like the same as the chemical one, but physical absorption itself are widely used method in CO2 removal unit fields because most likely in handling a high pressure gas stream, which is mostly associated with hydrogen production in steam methane reforming or SMR. The EU 2023 are mentioning on this journal mainly explain about that once being absorbed, the CO2 could be easily released from the solvent by reducing the pressure, so allowing the solvent to be regenerated and reused after. So the EU also mentioned that common solvent that used in the physical absorption are including Solexol, can be called as Rectisol with different main component in the compound, and also any other solvent that mainly can be used in the SMR fields. And the last part are the hybrid system. Hybrid system itself is not commonly known, but pretty well known and in the newest fields of SMR. The hybrid system of integrated are multiple energy generation and the storage technology, mainly to maximize the efficiency, reducing emission and enhancing the reliability of the process, which means hybrid energy can dynamic a clear switch between energy resources or simultaneously use them to meet the fluctuation demands of the process, which is ensuring the optimal utilization of the available resources, which can be explained by Zhao et al. 2023 in his journal that running one-dimensional modeling of this process and also mentioning several key components of the hybrid system itself. So the using of this hybrid system actually giving a lot of benefits such as reducing the emission but also enhancing the reliability of the process, which is giving a good impact to the SMR plants. That's all my explanation for the CO2 removal. Next, the H2 enrichment part will be explained by my other friends.
Hello, my name is Putri Ramadhani and we're going to the next section is about hydrogen enrichment. Hydrogen itself is a key to sustainable futures because hydrogen is emerging as a critical component in the global transition to cleaner energy and reducing greenhouse gas emission. The European Union has set ambitious climate target to combat global warming. So this includes reducing greenhouse gas emission by 55% in 2030 and achieving carbon neutrality by 2050. Hydrogen plays a vital role in achieving these goals as it offers a clean energy solution to decarbonize industries and transportation. And the strategy that European hydrogen use is to meet this target, the EU has developed the European Hydrogen Strategy. The plan focuses on producing clean, renewable hydrogen with specific goals of deploying 40 gigawatts of hydrogen electrolyzers by 2030 and 6 gigawatt by 2024. This strategy highlights the importance of building a market for clean hydrogen and advancing the necessary technologies. However, there are significant challenges, which is most hydrogen is still produced using fossil fuels, which undermines its environmental benefit. Additionally, low-emission hydrogen production methods such as renewable hydrogen are not yet economically viable. Overcoming this hurdles will require technology innovation and investment. And then we're going to talk about hybrid purification process. To address these challenges, innovative technologies are being developed, including a hybrid hydrogen purification process. The first step is use polyethylene oxide membranes, which selectively allow gases to pass through. These membranes have high CO2 permeability. It's about 15-18 GPU, and hydrogen permeability is about 195 GPU. The second step is compress CO2-rich gas stream to 10 bar to prepare them for further processing. The final step is the hydrogen cooled into minus 61 degrees Celsius, where CO2 solidified and removed, leaving behind high purity hydrogen. And of course, there is some benefit. The first one, it produces high purity hydrogen suitable for industrial and energy application. The second one is effectively remove CO2 and reducing emission. And last but not least, the system is scalable and aligned with renewable hydrogen production method, making it an excellent fit for the EU's clean energy vision. So for the conclusion of hydrogen enrichment, hydrogen is a vital part of achieving the EU climate goal. While challenges exist, technology innovation like the hybrid purification process are paving the way for clean and cost-effective hydrogen production. To succeed, we must continue investing in this technology to build a greener future. Okay, the next will be presented by my friend.
Okay, my name is Dzikry Aulia Atmadja. This for H2 enrichment unit, three kind calculations. For the first is mass transfer zone. Okay, for mass transfer zones represent the active zone within the absorption column where mass transfer occur before equilibrium is achieved. For the mass transfer zone in an absorption process is critical for determining how efficiently the system utilizes for the column. For the second one, column diameter calculations. For the column diameter is calculated to ensure it can handle the specified gas flow rate while maintaining a low pressure drop across the column. For the industrial hydrogen purifications, the article specify volumetric flow rate Q of 1 meter cubic per second and superficial gas velocity 0.2 meter per second. Third calculation is column height. The column height is determined by the absorbent mass required to achieve the desired separation capacity. The article provides an example where an absorption mass of 5,000 kg and a bulk density of 600 kg per meter cubic are used. This parameter results in a column height of 1.62 meter with a cross-sectional area derived from the calculated diameter. For the height, ensure that the required absorbent capacity is made to purify hydrogen efficiently maintaining scalability by ensuring the correct balance between column height and the diameter. For the calculated parameters, demonstrate scalability and practicality for industrial hydrogen purification process. Emphasize the importance of aligning theoretical calculations with industrial standard.
Assalamualaikum warahmatullahi wabarakatuh. My name is Alifya Safira and I will explain to you about the optimization strategy. We've developed an efficiency system to achieve 99.9% hydrogen purity while significantly remove CO2 emissions. Tailored for industrial scale application. The process uses a hybrid approach, starting with membranes to remove most the impurities with minimal energy use, pressure swing absorption, then complete the purification to achieve ultra-pure hydrogen, using advanced material to minimize waste and ensure consistent performance. For CO2 capture, the system adapts to different needs by incorporating amine absorption for large CO2 stream or solid sorbent for faster, more energy-efficient operation. Waste heat is recovered and reused, reducing energy consumption, while automated control keep the system running smoothly. The newer design allows for easy expansion or upgrades, and durable material ensure a long-term reliability with minimal performance, low energy use, and sustainability, setting a new standard for hydrogen production and carbon capture technologies. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Hello, my name is Yudha Pratama. In conclusion, this project advanced sustainable hydrogen production, achieving 99.9% purity while significantly reducing CO2 emissions. A CO2 removal unit utilizing the UNO-MK3 process with potassium carbonate demonstrators and change reaction kinetics, lower energy requirements, and also reduce volatility compared to traditional amine systems. The hydrogen enrichment process employs a hybrid approach, combining membrane separation for pretreatment with pressure swing absorption or PSA for fine purification. Key design features include a 4-meter mass transfer zone, within a 10 meter column and a 2.52 meter diameter to efficiently handle a 1 meter cubic per second flow rate. The integration of heat recovery systems, automate controls, and also modular design and change energy efficiency, operational scalability, and also adaptability for industrial application. This comprehensive low energy system sets a new standard for hydrogen production, aligning with global sustainability goals and supporting the transition to renewable energy. So that's all from me. Wassalamualaikum warahmatullahi wabarakatuh.